Hello everybody, this is Dr. Hassan again in Renewable and Sustainable Energy in Module 2 Photovoltaic and Solar Thermal. This is week number 5. I will talk about photovoltaic performance and their applications. More focus on application, but now the process contain some currents diffusion. As example, you can see diffusion of current flow of electrons from the N side to the P side and drift of current of electrons from the P side, the opposite. The same thing could be say diffusion of current of holes and drift current of holes from the N side to the P side. These diffusion and drift currents are here, you can see, represented by formula related to the charge of electron, concentration. Let me define these parameters. As you can see here, N and P are the concentration of electron numbers per unit volume, while Na and D is the concentration of acceptor and donor, the impurities. Ni is the intrinsic concentration, and Dn and Dp are the diffusion constant, electrons and holes respectively, N mu naught and mu n, mu n and mu p here, mobility of electrons and holes. Now, after I define let me say formula for each one of these drift and diffuse current, what we have is we can find the intrinsic, as you can see here, intrinsic carrier concentration Ni by this formula. What I want to take you through is to drive a model, a formula for current and voltage of the diode of the solar cell. Now the concentration represented by B, which is related to the effective mass, T temperature to the power 3 over 2 exponential Wg is the energy gap, and Kt, you know, they are Boltzmann constant and temperature again. Now the current, total current across the junction will be current from N side and current from P side, and at the end we say equilibrium, so there is zero current flow through the P-N junction. Now, if I take the formula in the previous slide and substitute for Ni and Np, we go, as you can see here, you got this formula, which we say equals to 0, because equilibrium. Now, from the definitions, from principles, we know that potential difference will be minus dV over dx, with respect to change of voltage with respect to the distance. Now, if I substitute this in the previous equation, I approaching here, now I want dP over P, these values, so I rewrite the formula. It look like in this way. Let me define this part, mu P over dP to be K Q over KT. Then I got this part. You see, remember this part is part of the formula of the current for the solar cell. I mentioned it in last week, in our session. Now rewrite the formula and put it in the final form. This is the formula in its final form. But just a minute, V, the voltage from Pn to the voltage from Pp, is the difference potential or voltage between the two terminals, positive and negative, coming from the solar cell, which is called contact potential. We call it Vc. We can't put it as a Vc directly, so this gives me the voltage on the contact at the end, because don't forget, photon come to the cell, produce electrical current. This electrical current should be collected by fingers and take them to the bars, and the bars at the end, the bus bars at the end, connected together to come up with only two terminal, positive and negative, represent the output of the solar cell. Now, let's use this formula in this example. He told you that the doping concentration of the particular silicon junction is Na and Nd is given to you. The operating temperature is 300 Kelvin, and the intrinsic concentration of the carriers is this value. What is the contact potential? We have the formula. Hey, K is a constant, Q is a constant, T is given in the question, Na, Nd and Ni, all of them are given, as you can see here in the question. We found it 0.72 volts for the cell. By the way, you need to know sense number, just for sense, that the cell voltage is supposed to be in this range, 0.7. If it is lower than this means that something the quality of the cell is not good enough. I mean, you can't judge your quality of your cell. One of the simple way, is to see the VC, its VC. If it is 0.7 plus minus in this range, is okay. But if it go to 0.6, 0.5, this means the quality of the cell it get manufactured. Now for current, we know that each photon, we mentioned that the photon is not necessary, by the way, the photon energy is enough to produce electron go to the conduction band from the valence. Some of photons energy is not enough. But let's talk about photon energy which produce electrons. Then we can write the external current produced by photon by charge of electrons, by flux density of the photon, by the unit area. Okay. Now if I take also this is the current, as I mentioned. This is the production of current from the photon energy came. Now the operation principle of the cell itself, it's p-n junction, so it's represented by diode, as you can see here, right? So then the current coming from here, part of it here and part of it going to the external load. So I can write I load is IV minus, very simple circuit, you know, you study this in secondary school even. Now I do it how we calculated. There is one known formula which called Shockley equation. Okay, Shockley equation used to calculate the current of the diode. So if I put it here, then I have a general formula for the solar cell, which is written in this way: IL equal I load, it means I load equal IV coming from because of the photon, or II they call it sometime, okay, by saturation current exponential, Q is the charge of electron, V is the voltage of the terminal, K is the Boltzmann constant, T is the temperature, -1. I can rewrite it again to make it voltage in terms of current rather than current in terms of voltage, okay, in this way. Now one more issue, you know the contact, the two contact, positive, negative, coming from the cell. At the end, these are material. They have resistance, even if it is small, but it's a fact. So I can consider it. Consider there is serious resistance, okay? And here the load. So there is a drop across the terminal. So I can consider it, okay, by subtracting this part from the total voltage. Now, if we have open circuit, no current in the load, then this part will be gone and this part will be gone, and the equation simplified for open circuit situation this way. Now let's put the general form. The general form of the general model of the solar cell is we have current source to produce electrical current because of the photon energy, diode to express the p-n junction effect, resistance of the terminal, we call it RS, series resistance, R shunt or parallel resistance, because of, you know, inside the solar cell we have fingers collecting the current to the bus bars, and here there is also losses. All these need to be considered, okay? This model called one diode model, it's more than 70 years being used by scientists, researchers working in the field, okay? Now for maximum power, I mentioned here in IV characteristics before that it's plotted in this way, this curve, okay? And by the way, it's supposed to be plotted in this way, but this part lose, the shaded part here lose because of the losses inside the cell. Here is the short circuit, here is the open circuit voltage, but the maximum supposed to occur somewhere here where we have high or maximum or peak current and peak voltage, okay? PV characteristics based on this can be plotted in this way, and again it's peaked at this point, okay? Now efficiency, we discussed the output over input. Now let's come to the applications. Now here I think you will enjoy more, because these applications, okay, show you what amazing, let me say, wide, let me say, range of applications available in our world using solar cell. We may don't know about many of them. Let me revise and give samples. Now we mentioned that the solar panels or modules could be used for utility or connected to the grid or standalone or tracking system, okay? Now, utility is very simple. We have the array here, PV module or array, or let me say plant, connected to charger controller to control the output voltage and power current coming from the cell. And if it is connected to the grid, then definitely we have inverter to convert the DC part here into AC part here and give it to the grid or to the load. Now, sometimes they use batteries for critical load. Okay. Here is, as you can see here, I try to take some photos from many places I visited and to show these systems for you. As example, here in Suhar city center, if you get there, you can find this PV make a shadow on the park, and they generate electricity and give it to the grid. The same thing here, Majan electricity company have their flower there on the top of their building, green building, and now it's moved to Majis. They took it and they put it there. Also in Suhar University, we have here, you can see our system. This is the grid connected system, this is standalone, this is tracking system. Okay, and the simple idea, we have PV, we have inverter, definitely protection devices, and so meters, all of them, these are protections. Then it come to the load through consumer units to the grid. Okay, but in general, PV inverter going to the grid. Now, for a standalone, it have many applications. We have, this is in Suhar University of the top of this building, as you can see here, and very, very simple idea. We have panel, we have charger controller and battery, and then either AC load or directly here from the charger controller to the DC load. Okay. Now, many applications are there here, even in Suhar University campus. I mentioned for this on the top of the building. I would like to mention for this panel here. Okay, these 6 panels, modules, connected together to supply electricity for a water pump. I will mention for it in the next slides. Okay, our student did this grant from Research Council of Oman, and they produce water. They got water from the well for aggregation sector. It's there near the female housing in the Suhar University. Okay. Now, also some of the application we can use it for lighting. This is a Suhar University, as you can see here, the panel, and this is in Masdar city in Abu Dhabi. You can see it. The examples, I just give examples. Otherwise, it's used in many lighting applications. As example, billboard, highway information signs. I would like to read from the slide. Public use facilities, parking lots, marine, homes, vacation cabin, pairs, cabots, lighting of trains. So these are many applications. Okay. Also, you can, I talk this in Turkey, maybe, yeah, in Turkey, you can see here for traffic lighting and for traffic light. Okay, and here in Masdar Institute in Abu Dhabi, here in Safa and Ibri. Okay, I took these photos in Safa and Ibri because these are isolated area. They need electricity and it's difficult to provide, but solar energy is best source of energy application. Another applications are using solar cell to provide electricity for communications. As example, radio, television, phone signals, and so on. Okay, cellular phone, portable computer system, mobile radio system, emergency call box system. And if you go here in Oman near the mountains, if you see the towers there, communication towers, you can find that they use solar cell, which is the base because grid connected, and grid it cannot operate there, or it's costly, really costly, and another source of energy, as example, diesel generator. Remote site electrification. There are many applications in remote sites far away from civilization. Example of this is rural homes, visitor center and park ranger site, vacation cabin, hunting lodge, remote farm, workshop, village and isolated electrification, clinic and remote research facilities, highway research stop, public bench, camp ground, military. So there are many applications in remote area need electricity, and the electricity they need is not that much for their application. So solar cell is the best to provide this electricity. Also remote monitoring in some applications, especially for research, okay, they need remote monitoring, okay, or let me say some application as example highway traffic condition, structure condition, seismic recording, irrigation control, scientific research. All these are remote monitoring systems need source of energy. Solar cell could provide the needed energy. Sign and signals could be for high warning signs, railroad signals, aircraft warning, backpack beacon, bios and lighthouses, and many other type of applications. I give here some photos for meteorological, as you see, station supply and park ranger site supplies by PV systems. Water pumping and control system. You know that there are many area need water. Underground water could be the best solution, but pump use to bring this water from underground need energy. The one of the best way to provide this energy is to use solar photovoltaic. Okay, solar photovoltaic, one of the best to use this. Here our students work on a project, techno-economical assessment of optimal design for photovoltaic water pumping system for rural area in Oman. And they design system, as you can see here, this is the PV system, this is the converter with a battery, okay, and it's taking the power to the load, which is the pump in the well, and this is the well, and then it pump it to storage tank, and then it give it to irrigation. Okay, they have many scenario, and they did a good simulation modeling and experimental validation for this system. It's already installed in Sohar University. They started here. I just want you to show their journey. They took this place, okay, the students prepare it, okay. Here they will have the aggregation part, okay. This is the well, this is the internal unit, okay, and this is cover for the well. After that, after they prepare it and clean it, okay, they started from the panel, they make the frame here, okay. This is Mr. Ibrahim Al-Ajmi, who was one of our colleagues working with us here, also Rashid, okay. This is one of our students, they are graduated. Ali here is Dr. Ali now in solar energy, working in UKM, National University of Malaysia, and now they put the frame to the location, they put PVs here, as you can see, okay. Then after they put the PV here, they start preparing the pipes for water flow with different valve here, sensor, automatic valve, okay, because these valves are electronic valve, okay. So they send signal, it will work, as you can see here. This is the water coming to the tank, and this is the control internal unit. It's work alone, we don't need to operate it by ourselves, just programmed, and we leave it so it know when it's send time to this or that valve to open the water and to get it to the required location. Here they make the concrete, here the internal batteries and converters, and look how it look like the area after they get arrange it, and this is the panel, and water coming in this direction. Under you cannot see it, the pipes, as you know, under this green area, and it's provide water since maybe 2015. Now also part of the application is charging vehicles batteries, okay. I try to take this photo in London, okay. As you can see here, these ships inside, they use PV, it's free, they just put over there, and there is battery inside, they charge all the time, they don't need to touch it at all. It's work alone. They use the electricity needed inside for lighting, to watch TV and so on, okay. Many application is there, okay. Disaster relief application. When disaster happened somewhere because of tsunami, earthquake, and other volcano and other natural problems, then you need a fast solution, and solution, you don't need to supply the fuel, okay. Fuel is free there, so solar cell is the best option for this situation. Cathode protection. As you know, when we put a metal pipe or any metals under the ground or in water, because of the soil and water, salty water, they get have corrosion, okay. because of the electrolytic action. So how we can prevent this corrosion? By using small voltage, positive voltage added to the pipe. They make it like positive, negative, and then prevent corrosion from happening. PV is one of the best solution, because you only need to connect it and that's it, done, leave it. It will automatically prevent electrolytic happening and corrosion come to my metals. Consumer products, many small let me say application. We know the calculator, small calculator. When students in the schools, they use calculator with a small cell there, but there are many other type of application for small application, as example watch, lanterns, radio, television, flashlight, outdoor light, security system, gate opener, golf carts, and fans. So there are many applications for refrigeration, especially in the isolated area or in the desert. Okay, PV is the best solution. We can use PV. We designed here maybe in 2002, one, I don't remember exactly. We designed a refrigerator for the desert applications. Okay, and the main source was photovoltaic, and here is the refrigeration. Okay, here are some photos for cooling and some application. As example, it's using air conditioning. This system now is widely used in the region, or it's cool. You see here, we use PV with a cooler, or here refrigerator. Here this one, refrigerator. This is another system, cooling system. This is also air conditioning. Now solar cell, as I mentioned, we connect them. You have the cell. You connect them series and parallel here in this way and this way to come up with a model. Putting model together, you come up with a panel. Putting panels together, 1, 2, 3, as example, you come up with an array or power plant. And this is the series connection, as you can see here, current from here in this way, or parallel connection.